Hello everyone, my name is Chai. Today I will present my paper which is titled Motor Synergy Development in High Performing Deep Reinforcement Learning Algorithms. Without any delay, let's start. First of all, we need to understand the concept of synergy in human. As we all know, in human there are a lot of redundant muscles and it will be very complex and redundant for the central nervous system to send signal to each muscles. This is too complex and redundant. In order to overcome this complexity, recent findings in human motion shows that humans actually make use of what we call synergy components to help simplify the motion control process. These synergy components encoded in the central nervous system will translate the signal from the central nervous system to control the muscles. So the central nervous system only need to send N signals to control K muscles, with N, the number of synergy, much smaller than the number of muscles K. This results in energy-efficient movement control. With the concept of synergies introduced, we are now ready to talk about the motivations of this paper. In this slide, we can see a typical control loop used by deep reinforcement learning algorithms to control an agent. For example, here we have an agent called half cheetah. We would like to investigate whether during the learning process, deep reinforcement learning algorithms also try to use synergy components as in human motion control. The questions that we are trying to answer in these papers are: does DRL policy learn to use synergy during training? And also, what is the relationship between synergy, performance, and energy efficiency development during the training process? As I've explained earlier, the motor synergy concept is a bio-inspired idea, comes from the researchers about human motion control. So we need to adapt this idea in deep reinforcement learning. In order to do that, I'm going to use the same technique as what have been done in human motion control researchers, which is using PCA to extract the synergy. I will explain it in figures, which is clearer to show you how the synergy extraction process is carried out in my research paper. First, at certain training checkpoint, I will take the partially trained policy to extract the control signals from this policy. Using these control signals, I will use a dimension reduction techniques called PCA, Principal Component Analysis, to extract the synergies from the control signals. At the output of PCA, I will have my joint synergies and also their corresponding activation coefficients. By using the extracted components, I can reconstruct the original signals, which is shown in red in the figure on the left. We can see that there are some errors between the red color reconstructed signals and also the original signals in blue. By using this reconstruction accuracy, I will define the synergy level. If we can have accurate reconstruction with few joint synergies, then we will say that this policy has high synergy level. This leads us to plot the following graph of reconstruction accuracy versus the number of joint synergies used for the reconstruction. At certain training checkpoint, we can vary the number of joint synergies or PCA components used to reconstruct the original signal. And on the y-axis, we have the R-square accuracy metric, which is a metric to measure the reconstruction accuracy of the signal. When this metric equal to 1, we have the perfect reconstruction of the original signal. So as we can notice here, for this training checkpoint, as the number of joint synergies increases, we can also see that the R-square accuracy metric increases. This is for one training checkpoint. If we take different training checkpoints throughout the training process of deep reinforcement learning algorithm, then we can associate different color to different training phase in order to have this figure to show the synergy development throughout the training phase. And as we can see here, as training progresses, the synergy level of the agent becomes higher and higher, and we need fewer joint synergies to reconstruct the original signal at the end. Hence, we can say that the motions are becoming more synergetic and coordinated through training. Now, let's see the video of motions of half cheetah throughout the training. At the beginning of the training, we can see that the movement of the half cheetah is rather random and non-synergetic. As the training progresses, we can see that the movement of the half cheetah is becoming more and more synergetic and more coordinated between the joints. And this is shown by the synergetic graph on the left side of the video. At the end, the joints are very coordinated and synergetic during the motion. Now, let's take a look at the action signals generated by the trained deep reinforcement learning policy. At the end of the training, we can see that there is a common phase between the joints for the back limb and also the front limb. And this phase is opposite between the back limb and the front limb. What this tells us is exactly that the limbs of the half cheetah is moving in opposite directions to move forward. And this shows that the joints of the back limb and the front limb are very coordinated and they are working together to execute the running motion. Hence, we have a very high synergy level between the joints at the end of the training. Let's analyze the result of the half cheetah experiments a little further. Here, I have plotted 3 different metrics on the same graph. On the horizontal axis, we have the training steps of deep reinforcement learning algorithms, and for the vertical axis, we have the scales for each metric. The first one is the purple curve, which is the surface area metric. This surface area metric is corresponding to the synergy level of the agent. For now, we are going to consider that this surface area is equal to the synergy level of the half cheetah agent. For more information, please refer to the paper. The second metric that I have plotted is the performance metric, which is the distance covered by half cheetah in 1000 times steps of simulation. And the last metric, which is the orange curve, is the performance energy metric. This metric is calculated by dividing the performance with the energy consumed during one rollout of simulation. Hence, the performance energy metric is equal to the energy efficiency of the agent. For this graph, I have taken the average of 15 different experiments of half cheetah, and I have also plotted the standard deviation of these 15 experiments, which is shown as shaded area around the average value of each metric. We can notice in this graph that throughout the training, the performance of the agent increased as well as the energy efficiency metric. These two metrics are the normal metrics that we use to evaluate an agent when we carry out an experiment in deep reinforcement learning algorithms. In addition to these two traditional metrics, I have proposed the synergy level metrics. As we can see here, the synergy level metrics correlates globally well with the performance and the performance energy metrics. This validates our hypothesis at the beginning of the study, which is, as the performance increases, the synergy level should also increase. Indeed, I have done experiments with 2 different deep reinforcement learning algorithms, namely SAC and TD3. For more information about these 2 methods, please refer to the references in my paper. The results of SAC and TD3 are plotted side by side with shared axes for comparisons. It is known that SAC algorithm performs better than TD3 in many cases, as well as the half cheetah agent case. We can see that the 2 traditional metric, the performance and the performance energy metric, performs better in SAC than TD3. This applies also for the synergy level metric. It is interesting to note that the synergy level development in SAC algorithm is much different than the TD3 algorithm. We can see that the synergy level of SAC algorithm is higher than TD3, and the development of the synergy level is more significant. This gives us some future directions, such as to design an algorithm with the concept of synergy incorporated, so that it has high synergy level, which may also implies that it also has high performance and performance energy level like SAC algorithm. It also shows that it may be possible to use synergy level metric to evaluate a deep reinforcement learning algorithm. As we have shown in our paper, the synergy level metric and its variants have successfully distinguished the characteristics between the high-performing SAC algorithm from the relatively less competent TD3 algorithm. This shows that the synergy level may be the factor for evaluating an algorithm for motion control. Thank you for watching our video. I look forward to answer your questions if you have any. Have a nice day.